All right, so this week we discussed the few concepts, 8 puzzle, BSDs, priority queues. So let's go over some of the ideas in this week's lectures and the precept. So we start with this idea of 8 puzzle, which is also your next programming assignment. The idea is that the 8 puzzle is played on a 3x3 grid with 8 squares labeled 1 through 8. And the goal is to arrange the tiles so that they are in order. So you go from 1, 2, 3, 7, 6, 5, 4, 8 to 1, 2, 3, 4, 5, 6, 5, 4, 8. So this is part of a sort of a idea of creating a program that can solve this puzzle. So the way we think about this is sort of like if you ask a computer to do this, the computer must think about what are the possible moves that you can make given this board. So for instance, this is the empty square. So I can move 3 possible moves. I can move 1 here, 7 here, or 5 there. So let's assume that I move 1. So the rest of the things remain the same. 7, 6, 5, 4, 8. And then let's move 7. So the rest remain the same. And let's move 5. So we will have 1, 2, 3, 5, 7, 6, and then 5, 4, 8. So now, so you can continue to do this and you can fill in the unfilled boards. And so that's a key idea in this part of the problem that keep solving. Like for example, if you go from here, you have 2 possible moves. You can move 1 to the empty slot or 2 to the empty slot. So at this point, I'll pause a little bit and then you can think about what to do. You can pause the video and complete the board. Okay, so let's take a look at the filled in boards here. So here is the picture I have after we do 2 levels of filling the boards. Now there are a few key things that are here that I will explain it to you, which is part of parts B and C. So in the parts B, we define what's called a Manhattan priority function. In other words, your goal is to go from here to the board 1, 2, 3, 4, 5, 6, 7, 8 board. So the question is, when do we go to that board? If you keep going down, you're going to reach one of the boards that's going to be 1, 2, 3, 4, 5, 6, 7, 8. But the question is, how do we know that we reach the board? Well, that's easy because you compare the boards here to the boards, the target board, which is 1, 2, 3, 4, 5, 6, 7, 8. But the question is, what is the process here? We can't just randomly look for boards. So let's think about what a priority means here. For example, our goal is to get from this board to the board 1, 2, 3, 4, 5, 6, 7, 8. This means that we should attempt to the distance between those 2 boards. So how do we compute the distance of the original board and how far it's from the final board? So we can define a number of functions that are called priority functions. So I will go over just the Manhattan, but you can find information about other functions in the assignment page. Now, one of the ways you know that Manhattan distance is defined like if you're given a tile, how far it's from the final place. So for example, 2 is supposed to be here, so it's like 1. If I make 1 move, sometimes you may have to make a move up and right or left, so horizontal and vertical moves. But in this case, if I move just to 1, then it'll be in the right place. So the same thing with 1. So let's say 1, if I move 1 to the left, it'll be in the right place. So I have to move 1 to the 1, 2 by 1, 3 is in the right place, 4 is in the right place, 5 needs to be moved to the left. So that's 1, 6 is here, and 1, 2, 3, 4, 5, 6. So 6 has to be moved up, and 7 and 8 are in the right places. So in this case, we define the Manhattan function to be Manhattan distance to be 4. Now, if you have the goal board, then the Manhattan distance for the goal board must be 0, because that's the goal board and you don't have to move anything. So our goal is to get to that. So here, what I'm going to show you is that, so here are the boards that has been completed, and let's compute the Manhattan distance for one of them. So let's suppose we take Manhattan distance here, 1, 2, 3, that's in the right place. 4, the 4 needs to go 2 places you have to go up and left. 5 needs to go 2. 6 is the right place. 7 needs to be here, so it needs to go 2 down and left. So you have 7 needs 2. And 8 is in this place, so it needs to go 1 left. So that gives you a Manhattan distance of 7. Now that we say the priority is also 7 in this case, because we compute the priority to be the Manhattan distance plus the moves. So let's assume that moves for the original board is set to 0. So therefore the priority for this element is 7. Now if you go to the next board, now you will find an easy way to compute that the Manhattan distance from this board. You don't need to worry about recomputing it. Like for example, the only thing that changed in this board is 1. Now in the previous board, the one did not contribute any to the sum, but now 1 does, because you have to move 1 up, so you have to add 1, so it'll be 1 more, and the priority is going to be the Manhattan distance plus the number of moves. So moves, we know to get to this level is going to be 1. Moves to get to this level is going to be 2. So we could compute that. Now if you go down further, you will see that the difference between these two boards is that so the one has gone back. In fact, you will find that it's identical to this one. Therefore, the Manhattan distance for that board should be also 7, but the priority is going to be 9, because that's going to be 7 plus 2. So this way you can compute the Manhattan distances. You can think about this a little bit and see if you can get all the distances here. We have computed things here. If you see any errors, just make a note. The priority is going to be 11 here. 7 plus 2 is going to be 9, and the 9, and the 9, and 7. And this board will have it's the same as the parent board or the grandparent board. In this case, the Manhattan distance would be 7, but the priority would be 9. Okay, so that's the completing that part B. The second one says circle the boards that will not be considered further. That is called the critical optimization. The critical optimization means you don't want to consider this board again because we have already considered this here. And therefore we need to remove the grandparent board from the list. So in this case, I will also remove this because that's not necessary now to consider. If you do, then it's going to get into an infinite loop. So you have to be very careful when you implement it. Just make sure that you do not put this in here. So this means you need to know some kind of a previous thing. Like for example, when you come to this board, suppose this is your current board you're considering, you must know the previous. So when you get the neighbors of the current board, you must not put the previous into a priority queue. If you read the assignment, you will realize that you need a priority queue to do this. Okay, so critical optimization is that. The other part of this algorithm is called the A-star algorithm. A-star algorithm is a greedy algorithm that try to execute the program by looking for the cheapest possible solution. So just to make things more clear here, I will display the A-star algorithm like this. Suppose the boards are named 0, 1, 2, 3, 4, 5, 6, and so on. So what you're going to do is you have certain priorities for each board, and you put them into a priority queue. So this means that I'm going to display the priority queue like this. In other words, I'm not going to worry too much about what's here in the tree, but I'm going to say that the first element that you're going to put into the priority queue is the board 0, which has the priority 7. And then you remove this is from the priority queue, and then you enqueue the rest of the boards into the queue. So you'll be enqueue 1, 2, and 3 into the queue, priority queue. Now in this case, you will have to decide who is going to be the root. So in this case, either board 2 or board 3 can be the root. So I'm going to choose 2, but it can be anything, and it should not affect the correctness of your program. Now once you get the 2, you will be looking at their neighbors. In other words, you're going to say, okay, let's put into the priority queue the neighbors of 2, because I'm going to pop 2, which is the minimum, and then put the neighbors. Well, when you put the neighbors, do not put 6, because 6 is the same as the grandparents that was considered before. So let's put 7, 8, and 9. So we put the board 7, 8, and 9. Now note that the priorities now, the board 1 has a priority, board 1 has a priority 9. And then if you look at the other boards, I think the board 9 is the one with the lowest priority, which is priority 7. The other ones have 9, 9, and 9, and so on. So I'm going to move 9 to the top. So this is the board that will be considered next. Okay, so you may also ask the question, why not consider 3? I think it's fine, but I think you should consider the whatever the priority queue is going to promote the next priority, which is 7 here, 7 here. So it could be either 3 or 9, doesn't matter. But that's what the priority queue will do. Okay, so the final part of this problem is that not all boards are solvable. So show that the following puzzle is unsolvable. Now, if you read the assignment description, you will notice that if n is odd, n equals 3 in this case, and to determine if the board is solvable, you compute the number of inversions. Inversions means that what elements are a's of I, when is a's of I greater than a's of j, when I is less than j. In other words, if you align the things row first, so you get 1, 3, 2, 5, 4, 2, 5, 4, 7, 6, 8. Think about this as an array, and if you sort this array, you're going to remove all the inversions. That means you have no inversions. If the array is sorted, you also realize that that's the goal. You must sort this array. Now, if you look at the number of inversions, so you'll see that this is not an. All right, so let's count the number of inversions in this array. So given the array 1, 3, 2, 5, 4, 7, 6, 8, we look at 1. 1 is less than all of these things, so therefore there are no inversions from 1. 3 is greater than 2, so there's 1 inversion there. If you take 2, 2 is less than all of these things, so there's no inversions coming from 2. If you take 5, 5 is greater than 4, but less than all of these things, so therefore 1 inversion coming from here. If you look at 4, 4 is less than 7, 6, 8, no inversions. 7 is greater than 6, so there's another inversion coming from 7. And but 7 is less than 8, so there's no inversion there. If you look at 6, 6, 8, 6 is less than 8, so it's all fine. So I'm counting the number of inversions here to be 3. All right, so now we have a theorem which says that if the board size is odd, and if you start with an odd number of inversions, and we claim that board cannot be solved. Now, how do we know that? So we argue that every time you move, so for example, if you move this 5 to this place, and it can change the number of inversions by an even number of things. In other words, it can either increase the number of inversions by a factor of 2, or it can decrease the number of inversions by a factor of 2. So what we are claiming is that if you start with an odd number of inversions, and every time you make a move, you add an even number of inversions one way or the other, add or subtract. And we claim that if you have an odd number and an even number, the answer is always an odd number. And therefore, we have the following. We claim that in order for the board to be solved, the number of inversions must be 0, but we consider 0 to be an even number. And if you start with an odd number and keep adding or subtracting even number of things, you can never get to 0. And therefore, this board is unsolvable. What is the growth of your algorithm? So the algorithm wise, I guess you can do a very simple algorithm. You start with I here and a j here. You fix the I, and then you compare how many of the j's are really, you want to know how many of the j's are really less than, less than a's of I. If they are, then you need to count that as an inversion. So if you keep doing it, then you move I to the next place and run the j through from here to the end, and you keep counting. So you can see that the first time you run n-1 times, n-2 times, n-3 times. So it's an n-squared algorithm. It's a quadratic algorithm. But in this case, the quadratic means that you're starting with a quadratic number of things. In other words, n is the board size. So it's really your n in your algorithm, it's n squared. So it'll be an n squared squared, or n to the 4 algorithm is the most sort of a naive algorithm that you can design. There is an algorithm to find the inversions in n squared log n squared, but if you're curious, there's no you can ask me about it, but there's no need for you to do that. You can just do a simple algorithm there. So you can find more information about the 8 puzzle by going to Salon and clicking on the 8 puzzle video. You can find a lot more information about the implementation of the 8 puzzle. So I strongly recommend that you do that. Okay, so the next problem is finding all the binary search trees that can be generated using a bunch of comparable keys, ABC. We assume that ABC are compared by the alphabetical order. Now, if you recall, there's a difference between a binary tree, which we call BT, and a BST. The binary tree means that any tree that has some sort of at most two children per node. But the BST has a different property. That means given a BST, we have an order property. In other words, every element to the left is less than the root. Every element to the right is strictly greater than the root. We do not keep any duplicate elements in a BST. And if you do have duplicate elements, you can use some sort of a counter to store them in the node itself. So there's no reason to keep any duplicate elements in a BST. So the whole idea of BST is just to maintain some sort of an ordered tree, so you can do a variety of things like finding things or finding the range of certain elements and so on. All right, so the first problem that we're trying to do is to draw all the possible binary search trees. So let's draw a tree like this, where you have C here and B here and A here. So in this case, note that the B is less than C and A is less than B. So maintain that order. So here's another possible tree where C would be here and A is here, which is less than C, but B is greater than A. And so here's another possible tree where you have A, and then you have C, which is greater than A, but B, which is less than A. So we have another tree which looks like this. We have A and B is greater than A, and C is greater than A. And then there's another tree that looks like this, which gives you B in the middle, A is less than B, and C is greater than B. Now, so we come up with 5 trees. Now, if you try to do more trees, you won't be able to do it. In fact, the number of trees is given by an interesting formula called the Catalan number, which is 1 over n plus 1, 2n, choose n. Okay, so if you simplify this, it would be n plus 1 and 2n factorial, and then n factorial, and 2n minus n factorial. And you can do some simplifications here. You will note that if you have 3 comparable keys, you can produce, according to this formula, you can work it out. There are 5 trees that can be produced. All right, so the next part is that we define, given a BST or given a BT, a binary tree, we can define certain order of traversal. In other words, we define 2 orders here, in order and pre-order. There's another one called post-order. You can read the slides to understand that. The in order means that so the in order traversal, you go to the left subtree, and then you go to the root, and then you go to the right subtree next. So that's the order of traversal. So let's see, you want to do this recursively. So I'm going to use the color red for this particular purpose. So in this case, you start with the root node, and then you have to go to the left tree. In the left tree, you try to go to the left tree, but there's nothing there. So if the left tree is not there, then you go to the root. So the D would be the first one you print out. And then once you print the root, and then you go to the right tree. In the right tree, you have to go to the left. And so the next one would be E. So this is number 2. And then you go to the root, that's F. And once it's done, so you did the left here, now you do the root, so that would be M. So then you do, you take this tree, and then you do the same order. You go to the left, there's no left, so you go to the X, which is going to be the 5th node, and then here you go to Y, this is the left of that tree, and then you go to Z finally. So the order is, in order, is going to be D, E, F, M, X, Y, Z. Note that this is a sorted list. So this is one of the tests you can do. So given a binary tree, if you traverse the tree in order, and it produces a set of sorted keys, if you assume alphabetical order, then you have a binary search tree. Okay, so let's do the pre-order traversal. I'm going to use a different color for that. Let's use green here. So pre-order traversal is that in the traversal order is that you go to the root first, and then you go to left, then you go to right. So let's go to the root first. So that's 1. And then you go to the left. In the left, you go to the root first. And then you see if there's anything on the right. There's nothing on the right here. So you go to the, so that would be the 3. So we have M, D, F so far. And then we go to the left. And in the left, we print the root first. That would be E. And then we go to the right. There we print the root again. So this would be the 5th node. That's going to be X. And then we go to Z. And then we go to Y. So this is your pre-order. All right, so just practice a few more problems like that to get familiar with the order traversals. Like I said, there are 2 other order traversals. The other one's called the level order traversal, and it's also something called post-order traversal. All right, so here's a challenging problem. Given draw a binary tree, not a BST, that produces the following order traversal. In other words, that we don't make any assumptions about the order of the keys. So we are given 2 traversals, and we got to figure out what the shape of the binary tree is. So the way I'm going to start this is by claiming that A must be the overall root of the entire tree. Now, if you look at A here, then I will claim that the left-hand side of A, because this is the in-order traversal, must have the nodes DCB, and the right-hand side must have the nodes NMTPQ. All right, and then now we have to figure out exactly how to split this. So DCB, who is going to be the root of DCB? Now I claim that the root of DCB, if I split this, would be D, because note that the D comes first. Now if I look at D here, C and B are to the right of D. This means that C and B should be here. So I'll try to split them further. Okay, so we have that. Okay, so now let's think about how the CNV splits. If you look at the CNV split, you notice that the B is the root of that tree. So I'm going to claim that B is going to be the root. And the C, because C is to the left of B in the in order, so C must be the left child of B. All right, so we have this root. Now we have A, D, B, C. Let's do the same argument on the other side. So we need to know, given this tree, who is the root. Now to get the root, I'm always going to look at the pre-order. Pre-order says, oh, P is the root. So I'm going to say, okay, so let's start with P. But if I look at P here, P is here. So this means that Q is to the right of P, because Q comes in the right side of the in order, and the NMT comes on the left side. So the NMT is here. So now we look at NMT and see how do we split this tree. So if you look at the NMT, you realize that M is the root of that tree. So we say, okay, M is the root of that tree because M starts here. And if you look at the M and N and T, you realize that N is to the left of N and T is to the right of M. And therefore you will have N here and T here. So finally we can say, we claim that the tree looks like this: A, D, P, M, Q, and then N and T, and then B and C. B and C. So note that the key goal of this problem is that given two orders, pre-order and in-order, you should be able to find the shape of the tree. Now, you can only do this with either in-order and post-order or in-order and pre-order. But if you're given pre-order and post-order, you will not be able to uniquely determine the shape of the tree. I'm also claiming that this tree is unique. There's no other way to get these two traversals from another tree. So you need to think about that. Now, one other thing you need to know is that if you're just given a pre-order traversal of a set of comparable keys, let's suppose these are comparable keys, then you should be able to find this without the in-order, because if they are comparable, the in-order means that you take this set and just sort it, and then you will be able to find another tree. So do this as an exercise. Just take the pre-order traversal, this particular traversal, and say, suppose these keys are sorted or comparable. This means that you can assume that the in-order is not this. It'll be A, B, C, D, whatever the order you get, and then you can come up with another tree. So I suggest that you follow that. All right, so let's take a look at the bonus problem. In the bonus problem, we have the following situation. That we are given a piece of code and we're trying to determine what the code does. So that's an important thing to understand here. So in the code, we create a max PQ. So this means max is at the top. We have the size of the PQ, which is the N is some sort of an array actually. PQ has a certain size, but A is an array, so let's assume that A is an array that we will use, and then size of the array is N. So we are taking an array and inserting a bunch of things into a priority queue, and we do that n times. So the question is, after you go through this, what does this code output? So let's think about this. Now notice that in the code, whenever the priority queue gets more than size bigger than k, you're deleting the max. So in other words, that your priority queue will never be more than k. And so you're deleting all these maxes. So you know that at the end, the priority queue will have only k elements, and you have deleted n minus k elements. So you have deleted n minus k elements, and the priority queue have k elements. But when we deleted the n minus k elements, you have always deleted the largest n minus k elements. So what the priority queue will print then is that it'll print the k smallest elements out of the n elements. It'll print the k smallest elements out of the n elements. Once again, the n is the size of some array, or you can think of a data set that you're going to insert. So the other question is, what's the runtime of the code? So let's think about this. Now you're inserting n elements into the priority queue of size k. So this means that to do this step here, so let's call this step number 1, you will have to do n log k operations. Notice that the priority queue is size k, and so you're doing n operations on that. And then you're deleting n minus k, so let's call that step number 2. You're deleting n minus k elements from a priority queue of size k. So this means that you have n minus k times log k, because each element will require log k operations because you have a priority queue of size k. And then you're printing the k elements. You're deleting the max that's going to cost you log k time. And so you're deleting the max. This means that you have k log k operations in step 3. So note that we have k log k operations because we are deleting k elements from a priority queue of size k. If you do the simplifications, you will notice that these two things cancel out. So you get 2n log k, and you can say this is tilde 2n log k is the complexity of that code. So suppose we remove this line here. So what will happen? If you remove the line, then what you're going to get is that you insert n things into a priority queue. So this means since you're not deleting, your priority queue remains size n. And then we delete k of these things. So you're going to get the k largest element. So if you remove that line marked here, so you'll get the k largest elements of the list of n things. So what's the runtime? So the runtime you can assess like this. If you don't have that, you insert n elements into a priority queue of size n. That would be n log n. And then you're printing k elements from that priority queue. So it would be k log n. Now, if you think about the tilde notation, you can say this is n log n in tilde notation because k would be smaller than n. So this concludes the precept 4. If you have any questions, you can post any questions into YouTube or to Salon.